Alright, so here we are in SolidWorks. Hopefully you've modeled up your shape, you've got it approved, and away we go. So here's my sphere with the sting mount attached. So I'm ready to go. One thing we need to point out right now to get this running right is the orientation. The way I drew it, my wind is going to be coming from the negative Z direction. So I've modeled this so that Z is where my wind is coming from, and it's going to flow in what would be the negative Z direction. So that's something important we got to pay attention to, depending on how you modeled your device, your shape. If you modeled it in the XY plane, then maybe it's a different plane, different orientation for you. So pay attention to where you've oriented your part in relation to the space that we're working in. All right, it does make a difference. So make sure you know that. So the first thing we need to do is to get this ready is come up here to our icon. That's a little gear, and we want to hit the drop down arrow and add-ins. And what that does is bring up this little add-ins box that allows us to turn on and off all these different features. I pretty much leave all mine turned off. So the startup column, I leave pretty much blank. This Forum 2019 I leave. I don't know why. But the rest of them I turn off because I don't need simulation every time or all these other things every time. That just wastes the computer resources. When I want it, I turn it on. So I leave these boxes empty. And so for flow simulation, I'm going to come over and check the box to the left of it and hit OK. And that's going to turn it on for this instance. Next time I close out SolidWorks and open it again, then the flow simulation will be turned off. All right, so it took a few seconds for it to load. I've run this before. I'm going to delete that run, so it's gone. And now I have this flow simulation tab. It's new, not used to it, and there the box disappeared. So this is my flow simulation tab. I've got a whole bunch of extra tools. There's also tools up here under Tools, Flow Simulation that I can get to now as well. So the first step is to hit this wizard button. We want to work in this to set it up easily. First thing it wants is a project name. So I'm going to call this sphere, if I can type, again if I can type, 10 miles per hour. All right, so I go ahead and hit next once I've put in a name that I'm happy with, which will be my sphere at 10 miles an hour. Then it wants to know what unit system we're going to work in. It's free for you to choose. SI is definitely easier. I'm going to pick USA. There it is set up things so that it's got velocity in feet per second, mass in pounds mass, length in feet, temperature in degrees F. One other thing, let's scroll down in here to medium properties. That's the property of the medium we're working in, which would be air. We're going to open that up, and density, it wants that in pounds per cubic feet. All right, that's what it's working with. So we got to keep those things in mind as we work on a few other things a little bit later on. Okay, so know what unit system you're in, know what the system is looking for, so that we can keep track of doing the right thing later. Then we hit next, and it wants to know analysis type. Internal is if we're inside the body or a pipe or a tube or any number of things that would be flowing inside of a body. We're doing an external one like this image here where we're flowing air around the body. So that's the only thing we need to do on the screen is click external and hit next. Now it wants to know what is our fluid we're going to work in. Well, we're working in air, which is a gas. So if I expand the gases, I'll find air near the top. And then I have to hit the add button. That adds it down here and takes care of it. So the next thing we want to do is hit next. And the next to last window is wall conditions. Just leave it blank. We're going to use an adiabatic wall, meaning there's no heat transfer happening, and we're not going to worry about roughness. So leave those alone and hit next. And here's our last window where it's important to know a few things. Remember, I talked about know what orientation you drew your part in, modeled it in, and how it relates to the physical space. So my wind, my velocity, I want coming in the Z direction, but I also want it coming in the negative Z direction. So up here, I'm going to enter my velocity as a negative number. It's coming from the Z direction, and I want it to be coming left to right So that has to be a negative value. So that's how we're going to take care of that, okay? So what is 10 miles an hour in feet per second? Well, I'm glad you asked. I've got a little calculator I set up here. 10 miles per hour would be 14.665 feet per second. So I can come in here and type in minus 14.665, hit enter, it'll throw my feet per second back on there, and now I've got my wind velocity set up. So it's very crucial you set this up correctly. And then I'm done with the wizard. I can click to finish. It's going to take a few seconds, and it draws this box. I'm going to try and zoom out carefully. I'm using a trackpad that's a little touchy. So you can see there was this box around it there. Got a nice view. This box is like the area in the wind tunnel that we've got our model mounted, right? That's a cubic box volume. So that's what this has created now too. And we can look at that in a little bit more detail. But first, let's go up here to Tools, Flow Simulation, and Global Mesh. And the settings here, it defaults at 3. Let's jump it up to 4, so it's a little bit tighter mesh, a little bit better results without bogging our computer down. If we went all the way up to 7, we'd have just a really tight mesh, but it would slow things way down. So 4 is a good number. Go ahead and hit your green check mark, and it set the global mesh parameter. What does that global mesh look like? Well, I can go to my Tools, Flow Simulation, Project, and then Show Basic Mesh. And so now it has shown that basic mesh on my 3 ordinal planes, okay? And each one just looks like a box, but each of those boxes represents a stack, in this case, of cubes. And each one of these boxes is just a stack of cubes over the entire height of this equation space that we're working in, simulation space. Or like here, these would be cubes in a row and cubes in a row this way. So this is just filling up this volume with a bunch of cubes. And what this simulation is doing is that each cube, or at the corner of each cube, it's going to calculate our wind velocity and a couple other parameters, and then go to the next corner of the next cube and share the results from the previous one and recalculate, and then go to the corner of the next cube and just do that again and again and again at the corners of each cube throughout the solution space. So you can see how it could take a while, especially if we set the parameter way high at 7. Okay, so 4 is a good one for an average computer. Shouldn't be too bad. So I've got that on. I'm going to go ahead and go back to Tools, Flow Simulation Project, and just turn that off for the sake of clarity so we can see things a little bit better. So we've got our simulation set up. We want to know what we're doing this for. So there's this parameter down here called goals. What are we solving for? So if I right click on goals, I can insert different kinds. And the first thing I'm going to insert is a global goal. So this is something that the package can solve for pretty much automatically, and there's a big list of them here. So I'm looking at this. If I scroll down close to the bottom, I'll see forces. And there's a general force and a force X, Y, and Z. So these are the forces and the directions that were of interest to us. And remember, I set my model up so that's coming from the Z direction, the wind is. So I want to check the box for force in the Z direction. That is going to be my drag force, right? That's where the wind is coming from. I've got my frontal area there. That's where my drag force is going to be felt. So it's the force in the Z direction that I'm interested in. And we can go ahead and click the green check mark. And now we can see under goals, we've got a force that we're solving for. So if I right click on that, I can come down to properties, and under the name, I can go ahead and change that to my drag force. So now I know that's what I'm solving for. You don't have to rename it. If you understand that's what it is, that's great. So that's my drag force. We need one more other goal. We want to solve for the coefficient of drag, which you could do on your own. Once you've got the drag force, you could just throw it into an Excel spreadsheet or do it by hand on paper, whatever you want. But I'm going to do it in the solver itself. Let it do the work for me. Okay? So if I right click on goals again, there's an insert equation goal. So if I click on that, what it does is open up this equation expression editor where we can enter our equation. What does our equation look like? Again, glad you asked. Let's go take a look at it. So the drag force is equal to the coefficient of drag times rho v squared over 2 times the cross-sectional area that is presented to the wind. All right, so we want to solve for the coefficient of drag, so we can go ahead and algebraically remanipulate that. So we solve for the coefficient of drag, and that's 2 times our drag force over the density of our air, the velocity of our air squared, and the cross-sectional area of our body presented to the wind. So C sub D should be a unitless number. And we looked at our unit system, we chose a unit system, so let's make sure our units work out. So if I build a unit train, I can see my 2 is unitless, that's a constant. My drag force would be in pounds force. My density I looked at before, and it wants it in pounds mass per cubic foot, so that's pounds mass per cubic foot right here for the density. Now velocity, it wants it in feet per second, so that's squared, so feet squared per second squared. And then my area, it wanted lengths in feet, so that would be square feet for my area. So C sub D is a unitless number. Right now that doesn't look too unitless. Not much cancels out, just a couple of feet, and I'm still left with an extra foot, and the pound mass, the pound force, and the seconds. So if I go ahead and add in the conversions, and these are the two that everybody loves, they've got slugs involved. So I know 1 pound force is equal to a slug foot per second squared, because it's slugs in mass times the acceleration due to gravity gives me slug feet per second squared, which we call a pound force. So that's going to get rid of my pound force and one of my extra feet and my second squared, but now I've introduced slugs. I've still got that pound mass. Well, I know 1 slug is equal to 32.2 pounds mass. And so now my pounds force cancel out. My 1, 2, 3, 4 feet in the numerator cancel out the 1, 2, 3, 4 feet in the bottom, in the denominator. My pounds mass go away, my second squareds go away, and my slugs go away. So I am left with a unitless number, but I've got this 2 in this conversion factor of 32.2, which means that my actual equation I want to solve for is going to look like this: 64.4 times the drag force over my rho v squared A. So that 64.4 is taking that 2 that was part of the equation times the conversion factor that we need to make everything work out. And this is for English units only right now. SI would be different and easier. Just pay attention to your units. Make sure you're doing the right thing. Okay? So 64.4 times the drag force over rho v squared A. So I can jump back over to SolidWorks and start building my expression. So my numerator, I like to put it all in parentheses. So open parentheses at 64.4 times my drag force. I can simply come up here and click on it, and it inserts it into my equation down here in the expression editor. And that's my entire numerator, so I can close parentheses on that. Hit the divide and open parentheses for the basement. So for the basement, I've got my rho. So what is the rho for air? Well, remember, you're going to be doing this in the wind tunnel, and in the wind tunnel, you're going to have different parameters, right? Depending on what the temperature, the humidity, the air pressure for the day, the temperature, all that stuff. So let's go find some good averages that we can use. So if I jump over to my Firefox browser and go to this tab, this is the Western. Oops, I hit it. Let me back up. So I went to air density online / track dash results / Western _ Colorado _ dragway. And what that does is bring up some parameters that they're measuring continuously. And this gives us the latest data for the area, what the temperature, relative humidity, and my air pressure is. So my parameters now have changed slightly from what I used earlier when I started recording the video. But you would take these, the temperature, the relative humidity, and your corrected barometer, and come over to the air density calculator. And I'm not going to change my values. These are ones I was using a couple hours ago when I started this, so we're just going to let those ride. but I go to omnicalculator.com/physics/air-density. And we've got this calculator where I can add my air pressure in inches of mercury. I could change that depending on what I've got, but inches of mercury was given to me on that other site, so that's great. Air temperature in degrees F. It was a little bit cooler this morning. Air type, moist air at 32% at that time. Calculated the dew point, and it gives me an air density and different units, but I want it in pounds per cubic feet because that's what SolidWorks wants it in. So it comes out to 0.07426. So if I jump back over to SolidWorks, 0.07426, 0.07426 are my units for that. So then I'm going to go ahead and multiply that by, I'm going to go ahead and multiply it by my area because, and I'll tell you why in just a minute, but instead of going rho v squared A, I'm going to go rho A v squared. Mathematically doesn't make a difference. I just like typing it in that way, and I'll show you why in a minute. So I've got a sphere. I made it a 4-inch diameter sphere because that's the volume I can work in, is at 4 by 4 by 4 inches. And so a 4-inch sphere would work. And I need to know the frontal area presented to the wind, which would just be the area of a circle. So if I jump over to this calculator, I calculated out the area of a 4-inch circle to be 12.566 square inches. Convert that over to square feet because that's what I need, and that's 0.087264 or 0.0873. So I can jump back in here and type in 0.0873, and now I've got my area, and we're going to multiply that by the velocity squared. So if you remember back, it was 14.665 feet per second is 10 miles per hour. And we need to square that. So if I hit the Shift 6 key for my little caret and the 2, now I'm squaring it. And that's why I wanted to write this at the end. I can close parentheses. And now I don't have to worry about my exponent there, that raised to the power of 2 being multiplied by my area. That always bothers me. So I like to make sure that that's clear, that I'm multiplying density times area times my velocity squared, and I'm not multiplying anything by the exponent there. So I just want to make sure that things are clear. So that's why I like to do it that way. So I've got my expression written out. I'm happy with it. The units that it's going to assign to it right now are in this box, and it would assign it a force because we picked this drag force, so it's assuming it's going to be a force. But it's not. It's going to be dimensionless. So if I click on that and scroll pretty much to the top, it's in alphabetical order, dimensionless LMA. I'm not sure what LMA stands for, but it's dimensionless. That's good. So it won't show any dimensions. I can also click in this box here and give it a name. This is our drag coefficient. I can type that in, and now I've given it a name. It's dimensionless, and the expression's right. I can hit OK, and it's going to save it, and here we are. We've got our drag force and our drag coefficient that SolidWorks is going to solve for us the whole time. We're ready to run. So what we can do is come up here to Tools, Flow Simulation Solve, and hit Run. This will bring up a little box here. You want to solve. You want to run new calculations. Do not, if you run this again, because you will, you're going to run this multiple times at different speeds. You do not want to build off of a continued calculation. You want a new one. And so make sure it looks just like this run window, and then you click Run. Give it a few seconds. It's going to take a few, but eventually we're going to see a little window pop up here. It should blink at us. So let's give it just a few. Here it goes. So if I click on that, you can see my solver starting up. It's got a progress bar down here. And so right now I'm just waiting for that to get to a certain state where it's actually starting to run the process. Okay, so now it's starting the process, and I've got this list of goals here. If this is not automatically turned on for you, it's just this little flag right here. So I can unclick it and that goes away, or click it and I can see my list of goals come back. So those are the two goals that I'm solving for. The drag coefficient, drag force. Gives me current values, as well as a progress bar. You can see the CPU is calculating up time as it's running. So this could take 2 to 2.5 minutes, somewhere in there, for this to run. So I'm going to let this go, and I'll get back to you when it's solved. All right, through the magic of video editing, we are done. It has run its process, and you can see the progress bar is filled up. Solver is finished. Took it 2 minutes, 2 seconds, so it's going to vary depending on the computer you're using. And we've got our current values for our drag coefficient and our drag force. You can see they're negative values. That's because of how I oriented my part. Remember, I've got my wind coming in the negative direction, so that's why my values have come up this way. So that's not a big deal, just because I know that's how I've oriented things, so I can interpret the results, and I'm happy with that. Those are good value, as far as I can tell. Those are good values based on other results that I've done in the past. And what I'm going to do is give you a word of caution right now. Go ahead and write these two values down now, or if you're building a table in Excel, type them into Excel, save them now, because coming back to find these later is actually a bit more difficult than it should be. So just write them down now, save yourself the hassle. So remember, this is drag coefficient, so this is going to be unitless, which displays no units, and drag force is in pounds force. Okay? You don't have to worry about the negative signs. If yours comes up negative, don't type them into Excel as negatives. Just know that they came from the negative direction. We're looking for the amplitude of these values, not the directional values. That's something that SOLIDWORKS is worried about. Okay, so we're done with this box, so we can go ahead and close it. That window is closed. Right now it shows that my results are listed for 1.FLD, so it named that run number 1. So I can right click on results, and I've got this unload. So I can unload those results, so I have no results now, and right click and load. And so what this will do is just load the latest results. Make sure, because if you run this multiple times by cloning or just changing parameters, you can have multiple results. So that, by doing that little two-step process, the unload and then reload, gives you the current results. So if I expand those results, I've got a whole bunch of things here. The one that I'm interested in showing you is a cut plot. So if I right click on cut plot and then click insert, it brings up this property box where we can change a few things. Remember, I changed my plane, so I want to display my results in the YZ or ZY plane, because that's the direction my wind is coming from. So I'll change that to the YZ plane. You can see that's the direction that my wind's coming from. That's where I'm interested in. I'm going to turn on these vectors. That's going to give me arrows that are pointing in the direction of the wind flow, as well as their length gives me an idea of the speed. So vectors, and I want those vectors to display the velocity, the wind velocity, not the pressure. So I can click in here and change that to velocity in the X direction, or Z direction, I'm sorry, because that's the direction I'm coming from. So velocity in the Z, and this little number here, number 10, is the number of levels. So basically how dense it's going to be. I can crank that all the way up to 255. Really shouldn't hurt anything. Just takes a few extra seconds to process. But it's going to have a denser field of those vectors. And I can go ahead and hit OK, and it's going to create my cut plot, which it may take a few seconds. There we go. So there's my cut plot. And if I change my view so that I'm looking at the front, oops, wrong view. So I'm looking at this side here. There, now I can see my vector field. I can see what the velocity looks like coming in. I can see my stagnation point. I can see kind of where this zone of turbulence is creating. So here's my separation boundary happening right here. And this is a zone of turbulent wake. All right, pretty cool stuff. And this is the thing that you could take the screenshot of. These colors and the size of and density of the arrows is going to change as you go from 10 miles an hour all the way up to whatever the top speed you're comfortable with, 140 miles an hour for our wind tunnel. So this is the idea of what the results are going to look like, and that's pretty cool. Okay, so we've run the results for one run. We want to run multiple runs, right? We need to do this at multiple speeds. So if I come to my analysis we've already done once and right click, I can clone it. And it's going to want to rename it by just adding a 1 at the end. So I can get rid of that and change this to, say, 20 miles per hour. And hit my green check mark, and that's going to create a new project at 20 miles per hour. It has all the same parameters as my 10 mile per hour. See, the results are not loaded because it hasn't been run. If I click on my 10 mile an hour sphere and bring that up, I can see all the results are already there for that. Double click on my 20 mile per hour. I haven't done anything yet. Okay, so what do we need to change? Well, let's go to this input data and right click on it and general settings. So remember, we used a wizard before, but now all that's pretty much set. We just really need to change a few things. So let's do that here. So it's still an external analysis type. That's all we need to worry about there. Fluids, it's still air. That's still loaded. Wall conditions, still adiabatic and no worries about the roughness. And initial and ambient conditions. Okay, here's something we need to change. Right here, the velocity in the z direction. I went from 10 miles per hour to 20, so now basically I just need to double this, and without getting real math centered, that would be 29.2, actually closer to 3. So now that's close to 20 miles per hour without being exact. I would say calculate it so you know what you're actually putting in. But so that's close to 20 miles per hour. Okay, so that's all I need to change there. So I go ahead and hit apply and okay. So those are new, but there's one more thing that we need to change. If you remember, our drag coefficient is an equation that we created. So if I right click on that, I want to edit the definition of that, because here we entered the speed manually in the calculation, and that is not going to update unless we go in and change it. So I need to highlight that and change it to that 29.3 that I entered for our new wind speed. So you have to do this every time you start another run at a new speed. Don't forget to change it in your drag or your coefficient of drag calculation. So everything else is good. I can hit the green check mark, and at this point I'm ready to run. So another thing you can do is just click this run. So it's going to run the active project, which is the 20 mile per hour. I click the run. Again, I want it to be a new calculation. If this is ever available to you, don't click it. Do new calculation, run, and then it should bring up that same window. That should pop up down here. And we'll see our solver. And again, if the insert goals table isn't checked, you can turn those on to see your goals. It takes a few minutes until it actually starts running the solver before we can see our goals. Alright, so the list of goals automatically popped up because I had it open the last time. And so now it's running the new thing, and we can watch it as it goes and see our new values get calculated, see the progress bar. And again, it should take roughly 2 to 2.5 minutes to run, depending on your CPU. So I'm not going to let this go. I'll let it run by itself, but I think I'm done for the video. That should be what you need to do to get your shape calculated in the CFD and get your drag force figured out and your coefficient of drag figured out. All right. If you do have questions, feel free to stop by sometime in office hours. I guess I'll see you guys later.